So everyone, good evening and welcome to the another session in the data series. We are thrilled to have you here this evening for an interactive learning session. I, Neha Sen, part of the data science team at Analytics Vidhya, will be moderator for the session. So for those who have joined us for the first time, a brief introduction about the DataHour sessions. With the intent to make learning data science more engaging to the community, we begin with our new initiative, DataHour, which is one dedicated to data. DataHour is a series of webinars led by top industry experts where they teach and democratize data science knowledge. Now on to our session today, which is anomaly detection using NLP and predictive modeling. In this data session, Paritosh will cover the fundamentals of anomaly detection and discuss its application in job management and exception handling. Rather than proposing a single approach, this session will identify the nuances that should be considered while designing an anomaly detection solution. The session will be aided by real-life examples that leverage NLP, predictive modeling, and other ensemble methods to identify, correct, and prevent anomalies. Before we kick things off, and I hand it over to the session presenter, a quick recap of a few things. First, we are recording the session and we'll make the recording available in a few days on our YouTube channel. Second, please use the Q&A section for asking any question you might have during the session. As the data progresses towards the end, we will do our best to answer them. Third, also we'll share a feedback poll towards the end of the session, which I request everyone to participate in. Now, on to our speaker in the session of DataHour, we have Paritosh Sinha with us, Senior Data Scientist at Uber, problem solver, quick learner, and experienced team lead. Paritosh is a tenured data scientist with 10 plus years of experience in using machine learning, statistical, and NLP techniques to solve business problems across consulting, services, and product-based organization. He's currently working as a senior data scientist in the marketing division at Uber. You can follow him on LinkedIn. I'm sharing his LinkedIn profile in chat. Over to you, Paritosh. The virtual stage is all yours.
Thank you. And thank you for the introduction as well. I hope you can hear me clearly.
Yes.
Yeah. Okay. And I hope my video is working well as well. Yeah. Okay. Cool. So nice to see a large group of people joining us for the data series today. I'm Paritosh. My introduction is already done, so I won't do it again. The focus for today is on anomaly prediction and how do we use that and how do we execute that using NLP and predictive modeling. The one thing I want to really focus upon is today's data. I will focus on a lot of real life examples and how I have solved it based on my previous experiences. So I would love to have a discussion around the approach. There is no right or wrong. As I've always said, it all evolves based on the requirements. And I'm looking forward to the discussion. So let's get started. Yeah, I'll share my screen.
Yeah.
Okay, great. Okay. Yeah. Okay, I hope the slide is visible before I start. I just want to confirm.
Yes, it's visible.
Okay, cool. So yeah, so like I mentioned, the focus today is on anomaly detection. The domain on which we'll be focusing is software engineering. So a lot of product-oriented companies also are deploying anomaly detection solutions to essentially automate their operational processes and ensure that there's an intelligent layer into it so that the human element is reduced, right? So there are three parts or there are three items in the agenda. Given that nearly 80% of the audience is new to data science and machine learning, less than 3 years of experience. I'll do a quick refresher on anomaly detection. That should take us around 10 minutes. In the next phase, I'll then quickly jump into the use cases and software engineering. So I'll talk about two. And like I mentioned, this will be more interactive than anything else. And when we are discussing a use case, we'll discuss the problem background, we'll discuss the approach, we'll discuss the potential solution, and then we'll discuss what kind of a performance did we achieve when we implemented this approach.
Sorry to interrupt you, Paritosh. Your voice is, quite low. Can you please speak a little bit louder?
Okay, let me try that. 1 second. Is it any better by now, by any chance?
Yeah, it's better.
Better?
Yes.
Okay, great. Yeah, I was mentioning, if just to do a quick recap of the agenda, so we are doing a refresher on anomaly detection. Second, we'll be focusing on the use cases in software engineering. So I'll talk about two, and then we'll reserve the last 10 minutes for Q&A. Yeah. So let's start with it. So what is anomaly detection? Let's just start from there, and then we'll move forward. So anomalies are data points that display an unexpected behavior against usual patterns, right? So the thing I want to focus here on is one, unexpected behavior, and the second one is usual pattern. So the whole exercise which we'll be going forward with will just focus on these two elements. So one, we need to establish what's your baseline or your expected pattern or baseline behavior, and then we'll be looking at which set of data points or which group of data points are not behaving based on the pattern which we've already established. So that is all anomaly detection is all about, right? Why is anomaly detection important? Because there are two things to it. One, it gives you a signal on what are the underlying background conditions which are causing the anomaly to happen. So to give you a very real example, think of anomaly detection in a manufacturing setup. If there is an equipment failure, that is not just an equipment failure, but there are certain background conditions such as raised pressure, increase in temperature, or some behind processes, background processes which are not functioning well, which is leading to an anomaly. So it's not just about the anomaly, but what are the events leading up to the anomaly. Right? The second thing is, once you've established the anomaly, once there is some expected deviation from your behavior, from your normal behavior, what you will see is that downstream processes will also be affected, right? And that is where the impact kind of cascades, and like there is no controlling the final outcome. So that is the reason why first we detect it, and then we also want to predict something so that we prevent failures from downstream processes also from happening, right? And like I mentioned, so like detection is simply the process of identifying those past and predicting the future anomalies to prevent recurrence. So that is important. We focus on identifying the anomalies, and then we prevent the recurrence of the same, right? Now for this exercise, what are the key characteristics of those anomalies which you're trying to detect, right? And this is a little bit tailored to what you will see in the upcoming slides as well. But these characteristics of these anomalies are essentially, these are quite sporadic and rare. So usually the occurrence rate will be in maybe say early single digits of a percentage and maybe lower, and you will never see double digits or higher percentage for anomaly rate, right? So that is why it will be sporadic and rare. The second thing is that the anomaly should be traceable. By that, what I mean is, given this is a data-centric exercise, whatever we're trying to do is we are trying to either identify or predict or do both. We need to trace the anomalies specifically when they happen and what are the conditions around them, right? So that is where the anomalies should themselves be traceable. It cannot be a vague understanding of, is this an anomaly or this is not an anomaly. An anomaly should be defined based on the rules and business rules, and we should be able to trace a particular anomaly. And naturally, if you're able to trace it, the second piece of information is, once you identify an anomaly, you need to have some background information, because that is the whole essential construct on which you will either detect an anomaly or you will predict an anomaly. So what is an anomaly and what are the events leading up to an anomaly? Both of them are really important. And finally, whatever data you have captured, it should be explainable. By that, what I mean is, there are the anomalies, because they are the event rate is so low, or their presence is so low, there are often multiple external conditions where which you're not able to factor in while building the anomaly detection or prediction model. And that leads to higher failure of these use cases, because if you don't have the underlying factors which explain the anomaly, you will not be able to either detect or predict it accordingly. So that is where the anomalies which we'll look at will be sporadic, kind of rare. It should be traceable. It should be background information, and they should be explainable as well, right? Um, Quickly jumping into some common anomaly types, what you will see is there are three types of anomalies which we'll mainly focus on in this particular session, and generally the anomalies will fall under these three regions. One is global anomalies. So global anomalies, as you will see from the visual as well, global anomalies are those data points which assume a value which is far from the expected range or the general range of it, right? So there is no context to it. It's just an absolute value identification of what does the range of values look like and what is way higher or way low, right? Contextual anomalies are those where we need to take care of multiple factors while identifying what's an anomaly. So a contextual anomaly will be, for example, dependent on the day of the week, time of the day, the weather conditions, right? So there are a lot of external factors which will influence the presence of the anomaly. And finally, collective outliers are those set of outliers which not only focus on one point, but focus on a group of points showing a big deviation. So, for example, if you look at the chart here, you will see that there is a flat trend almost, but there are a group of data points which are showing deviation from normal behavior, and that is why these are collective anomalies. So, every time you're trying to execute an anomaly detection exercise, we should be one careful about what type of anomaly it is, and also try to understand what's the context behind it so that we create the approach of it, right? Um, okay, so let me move forward. So just yeah. So let's now deep dive into the use cases which I wanted to focus upon. These use cases, like I mentioned, are mostly in the software engineering domain. There are two which we'll talk about. So I've tried to bake in as much as real life data and visualization as possible. But yeah, I'm obviously restricted by the privacy needs of my org. But yeah, I've tried to ensure that you guys get the context of what we're trying to do, how we do it, and what was the final impact. So let's look at the problem overview, which I'm focused on the first problem. So the first problem that's going back is focusing on anomaly detection in data ingestion jobs, right? So how does it work? So the background is there's a marketing division wherein data from multiple partners, and these partners can be something like Google, like an Apple or a Facebook, which essentially track and share data for uh, for advertising spend and advertising revenue. So what they do is we capture this data from different partners. Now there are multiple partners, and like there are 100 plus partners, and the data ingestion process happens early. So naturally, what that leads to is there are anomalies in the data ingestion process. So think of it this way. So for example, if you're trying to understand, so you have spent certain dollars on say Google, and what you want to do is you want to understand what is the kind of conversions you're getting from that same particular dollar value. So what Google will share is what's the amount you spend and what's the kind of clicks. It's all rolled up. And that information will be shared early, so that because the data is quite huge, we cannot do a one-time download or a one-time ingestion into our tables. So that data is ingested early, and that is what helps us to track what's the spend, what's the conversion, and what's the expected revenue from our ad spend, right? Now, given the complexity, because there are 100 plus partners, there are 24 injections happening daily, like 24 hours. So there are 24 injections happening daily. So what happens is that often either the data ingestion is corrupted because of the underlying data sources not being correct, or due to server issues, there are cases where the data is not imported correctly, or the full data is not imported. So in that particular case, we'll see a big deviation in the normal behavior versus the expected behavior. or in the imported data versus what the expected behavior is. And that is what is the core problem which we want to solve for, right? The the underlying problem, and what also happens in a real life scenario, is the data is being used by business teams, and often the software engineering or the engineering folks don't have a tracking mechanism to identify what is the data set imported correctly or not, or are the data sets ingested correctly or not. And that is where the downstream business teams, when they analyze, when they create the reports, often realize that there's a big deviation from what they're expecting, or the values have changed quite significantly. And that is where a process is required before the data actually reaches the business teams to ensure that um, one, there is not enough delay. So, for example, say if the business team is using the data 3 days from the time of ingestion, so there's not a 3-day delay in identifying these anomalies. And two, once that delay has happened, the process needs to run again because the data needs to be ingested again. And that is, these are the two things which we want to avoid. So we don't want to, we want to minimize the delay in anomaly detection, one, and once the anomalies are identified, if it is done on the runtime, we can automatically re-trigger these scripts rather than waiting for the 3-day delay. So that's the problem overview. Now, what are the challenges which we need to consider while we are devising the approach for this particular problem, right? One, the occurrence of these anomalies are quite rare. So if you think about it, there are 24 into 520 plus injections for the 100 plus partners I talked about. And what we need to, and like the occurrence of these real, occurrence of these the occurrence of these failures is quite low. So you will see roughly 2 to 3 anomalies per week for more than say 12,000 ingestion partner combination. So that is where the occurrences are very low, but the downstream impact is very high because, for example, if you're not able to track what's the marketing spend correctly on your Google channel, or if you're not able to track what's the conversion from the Facebook channel, the downstream business impact and even the decisions which are taken going forward will also be impacted. So one, the occurrences are very low. The second part is the data displays a seasonality and a trend pattern. And you will see this as we move to the other details. But what essentially happens is that we do not have an absolute criteria which can be used to identify these anomalies because going back to the types of anomalies we discussed earlier, these anomalies are mostly contextual anomalies. So we need to take care of the context while identifying the anomalies and flag the corresponding partners or the corresponding engineering folks. The third part is, given the number of injections which happen every hour, this cannot be a very complex solution which requires many hours or many minutes to run. This has to be a low latency solution. This has to be integrated with the engineering ingestion APIs, and the anomaly alert should be raised quickly, right? And finally, each partner, our data with each partner will have a different trend, right? So the detection technique should work across multiple use cases. So think of it this way: your spend on Google will be different. Your spend patterns on Google will be different versus your spend patterns on say Facebook or on say Snapchat. And that is what needs to be taken care of when we are devising the approach. It cannot be that we have a specific one approach for each of these partners. That cannot really work. That cannot really scale. And that is where we need to ensure that the technique should work across multiple use cases. The potential impact, as you guys might have guessed already, it's multi-million dollars because one, the business teams get impacted, the type of decisions which are taken, they also get impacted, and the delays are pretty huge. That is where the exercise becomes really important in an engineering org, right? So now that we have the problem context, let me talk about the use cases I was referring to earlier, right? So these are three types of use cases what you will see, or what I observed in the data. One, if you look at use case one, it's essentially showing a very seasonal pattern with some big anomalies in this particular region, right? So that is where we want to, and there are other anomalies in these particular areas as well, where the data points are not showing where they are showing quite an expected a big deviation from the regular values. So that is kind of use case one. The key thing to note is that there is kind of no trend in this particular data. You will see it's mostly flat across a longer period of time, right? The use case two. So think of use case one as data being imported from or ingested from one partner. Use case 2 is data being ingested from another partner. So say if you're looking at your spend on Google, so your spend on Google will, for example, follow this pattern, but your spend on Facebook will follow a different kind of pattern, right? So if you look at use case 2, what you see that the anomaly types are different. Now, why do I say that? And for clarity's sake, I think there are questions. I'll come to the questions part in the end. So let me, or should I take care of it right now? I just wanted to check with the analytics with their folks. Team, could you help me out? Could you help me out? Should I take care of the questions now, or should we do it at the end of the session?
As a wish, as a wish. If you want to take it right now, you can take it, or you can take it at the end of the session.
Okay. Okay. Okay, so let me take care. Okay, let me actually do it at the end of the session. Otherwise, you just break the flow. But yeah, it's good to have these questions coming along. So if I look at use case 2, the scenario here or the kind of context here for anomalies is quite different. Just um, do not consider the red points for now. I'll talk about those red points later. But if you look at the blue curve, what you will see is that there's a fairly flat line for on what the pattern should look like, but then suddenly there's a big dip. And post that again, then you will see kind of a flattening pattern of what the data range should look like. And that is where we don't want to, in this particular use case, we did not want to classify all of the points from here as an anomaly, but we wanted to see where the dip was. And then if the pattern again becomes stable, we don't want to say that's an anomaly, right? Which is again very similar to kind of use case 3, wherein you will see that we don't want to classify all the data points within a particular range as an anomaly. So if there is a big shift, but that shift is retained, we should be able to consider that shift and only classify those shifts as anomalies rather than classifying the whole data curve as an anomaly. So the kind of expectations from the algorithm changes based on the use cases, which are essentially what kind of data we're tracking from each partner. And to give some idea of to give some kind of an idea of what the kind of complexity looks like, the pattern of spend from Google will be different from the pattern of conversion from Google will be different from the pattern of conversion from Facebook. So each metric and each partner will have their own customized pattern. And the trick here is to ensure that the anomaly detection algorithm works at scale, and there is no particular, like, we don't need to customize really heavily based on each partner and its own combination, right? So now just moving on. So now that you have a view of what the problem is, you have a view of what the data patterns look like. The approach here was pretty simple, right? It's a 3-step process which we are using to identify the anomalies. A lot of techniques were really taken care or were considered while designing the approach, but these 3 steps were forming the core part of it. So let me talk about each of the 3 steps in a little bit more detail before I focus on the specific approach. So initially, because the data is raw data, so you will have some kind of geography, you will have some kind of cluster of the user, and then you will have their corresponding clicks and so on and so forth, because it's all rolled up data. There is no specific data for a user which is ever tracked. So that data is essentially rolled up at a weekly level or at a monthly level or on a daily level. On how you want to identify those anomalies, right? So the metric is rolled up. Either it is sum of spend, it is total number of conversions, is it the total like the total gross bookings, either it's the expected gross booking. So there are multiple metrics which are computed either at a daily, weekly, hourly level or at a higher level to perform the anomaly detection exercise. Now the anomaly detection exercise itself focuses on 2 particular items. One is classical seasonal decomposition, because you will see in most of the curves below before, if I refer to these curves, you will see that there's a seasonal pattern to it. It's either weekly, it's either monthly, but there is a seasonal pattern to it. And all of these anomalies in this particular case are contextual anomalies. So we need to take care of context while identifying whether a data point is an anomaly or not, right? And then finally, once the seasonal decomposition is done, then we can take care of some simple rules to look at whether data point is anomaly or not by just looking at whether it is falling within the range after the seasonal decomposition part is accomplished, right? And finally, once the anomalies have been detected, the idea is that we trigger an email so that we are able to either notify the business owners or notify the engineering teams, either re-trigger their scripts, right? Or for business teams, essentially wait before they take their further business decisions. So that's a high level overview of the approach. What I wanted to do was I wanted to focus on these two particular elements. I think that is the core part where the group will be excited a lot. So let's deep dive into these two elements. So if you look at the approach, let's just talk about the first element, which is classical seasonal decomposition. This is something which folks familiar with time series forecasting or someone who has removed seasonality from their curves will really associate with. What we will see is that if you look at a particular curve, there are two elements to take care of, or two items to take care of. One is the seasonality, which is nothing but a repeating pattern across days, months, or say across years, right? And then there's a trend pattern. So for folks who are not aware with the seasonality and trend pattern, think of your sales in a particular retailer store, right? So what you will see is that the sales in on Saturdays and Sundays is higher when on weekends is higher when compared to Mondays to Fridays. So, and there is a trend, there is a shape which the curve will follow. So you will see the numbers being higher on Saturday and Sunday versus on weekdays, right? That is kind of reflection of seasonality. And again, the second point regarding trend for retailers who are growing. So think of like an Amazon, think of some other big retailers, maybe a Flipkart in India. You will see that their sales are gradually they increase over time, right? And that is another trend which we want to capture. That essentially is trend. You will see that the values are gradually moving up while following the seasonality pattern. So these are the two items or elements which we need to take care of to essentially perform this particular step, the classical seasonal decomposition within AD TK toolkit was used. And what you will see is that what's the kind of effect this package has on the particular data. So if you see it on the left side, let's assume this is say spend from a particular partner. What you will see is that once the seasonal decomposition toolkit is applied, the seasonality is completely removed from this curve, and you only have deviations from say a baseline which are being captured in this particular curve. Now the key thing to highlight is that if a curve is perfectly seasonal, you will see a flat line on the yellow side, but that's not happening because there are certain deviations from a kind of a flat line which happens post seasonal decomposition. So that's regarding seasonal decomposition. Once the seasonally decomposed curve is obtained, what we do is we implement an interquartile based assessment. So what we do is, and again, talking statistics will be really familiar with this. We take the 25th percentile, we take the 75th percentile. We use that interquartile range, and then we designate all values which are say 3 times above the interquartile range from the 75th percentile or 3 times below the interquartile range from the 25th percentile as outliers, right? Again, I would love to deep dive into this more if you guys want me to. But yeah, the package used here is interquartile range AD, and again the AD toolkit. Now the core idea I wanted to emphasize on is that implementing this package straight away won't have given us the desired result because there is a context which you need to take care of. So essentially what we're doing is using the CSD, classical seasonal decomposition, we're removing the context from the curve. And in the second part, once the context is removed, we're looking at the range of data points to flag out those anomalies which you can see in red. So that's the whole approach. In terms of once you've designed the approach, we want to ensure that we can also track the performance, right? And performance, when we are looking at in a software engineering context, is not just about what's the precision, what's the recall, but it's also about how much time your step is taking to execute and how consistent is that particular performance or your metric across different use cases. So that is where what we did was we kind of implemented a simulation methodology. And I'll just talk about this in a little bit of detail so that it's easier for you guys to also implement it if required. So think of this particular curve, right? When you're trying to assess what's the whether a given point is anomaly or not, At first, when you're trying to create the approach, you will have some designated set of anomalies already present. So you can validate the approach which you have in your place, right? Now, the way to assess whether your curve is able to, or whether your approach is able to meet the required performance or not, is to simulate only till the data point on which you have the anomaly. So, for example, let's look at this particular data point. If you know that this particular data point is an anomaly when you're kind of training your data set or trying to finalize your approach, you will only use these data points before that to identify, to predict whether this point is a data anomaly or not, and you will not feed the whole curve to the particular algorithm. And that is how the whole simulation methodology works. So for every data point in red, which you see here, only the previous 15 to 20 data points or previous n data points are used. Uh, Only the previous n data points are used. Only the previous n data points are used to establish whether the current ingested data point is an anomaly or not. So if I have to just move forward, so you will see, for example, for a date D1, you have a value V1. For date D2, you have a value V2, and so on and so forth. For date D17, you have a value of V17. So what the test does is you first run a test one on the first 15 data points. So you look at the trend and seasonality from 14 data points to establish whether the 15 data point is an anomaly or not. When you move to test two, you consider all the data points before that, and you look at whether the value on D16 is an anomaly or not. So that's your test two. And similarly, test three is on the first 17 data points to establish whether the data point D on date D17 is an anomaly or not. Now, a common question I've always faced is why look at different number of data points when you're trying to assess a pattern? Why not look at 15 data points consistently? The idea behind that is we want to increase the information being fed while we're detecting the anomaly. There is no fixed pattern here in terms of what fixed number of data points you want to consider. So either it's 15, 16, or 17. So that really changes it. The benefit of using a simulation methodology when we are trying to factor this in is it really gives us a real life simulation of how our model or algorithm will perform when it is deployed, right? And it will ensure that we are not factoring multiple data points from previous time period and the upcoming time period when we are establishing an anomaly, right? And obviously, it also enables a long-term data access for anomaly detection. So, like I mentioned, it's not a rolling window. We're taking a longer window into consideration while we're predicting the anomaly. And the approach gives us very good results. So it gives us 95% plus recall. It gives us less than 10% false positive rate across multiple use cases, and the compute time, like you see, is fairly low, so it's nearly 5 milliseconds, right? So that's about the use case one, right? I hope you guys have gotten an idea of what the approach is like and what were the potential results from the same. We'll do a little bit of more discussion at the end of the session once we open up the Q&A, right? The next use case is creating a self-healing system using system logs. Uh, this is a very interesting problem to solve, and the reason why I'm saying it's an interesting problem to solve is because the kind of data which we have, it's unstructured, and we need to really figure out how do we create those features out of unstructured data to give them non-detection. So the idea here is, and again to give some background, so we are working in the data engineering division that uses Spark uh, to ingest the data to do data manipulation and do feature engineering. Each data set which is ingested is run through a job. So it's a Spark job. And the one interesting point here is that there are multiple layers of dependencies across these Spark jobs. So if you're familiar with any schema, if you've worked with any database, you'll notice that there are multiple second layer of tables which are dependent on the primary tables. And hence, similarly, the second level of jobs are dependent on primary jobs. So there is a parent-child relationship of these jobs, and these jobs have in sequential order of execution. So that is the challenge, that is the context behind how the jobs are run, and also how the jobs are executed. So there's a sequential order of execution, and then there's a parent-child relationship. So if your parent job fails, the child job will also fail, right? So what's the business problem? The business problem is that your jobs observed were close to 2 to 3% failure rate, and these failures can be across different buckets. So it's either a syntactical error in the script, it's either that there are multiple jobs using the same resources, the resource constraint or resource usage problem. Either your parent job itself has failed and hence your child job is failing, or there are some other custom errors which can be defined by the engineer, right? And the key problem here also is that there is no mechanism to perform an early anomaly detection. Like you will realize, to perform early anomaly detection, we need to analyze the log files of the job when we are running the particular job. And so that is where we need to ensure that we create some amount of data from the job, while the job is executing, to ensure we are able to detect them. The challenges, some of the key challenges which we saw was that the data engineers, they had to manually skim through job logs to identify the reason for failure and then accordingly re-trigger the script. So for example, if it's a simple resource usage constraint, so what you do is you look at the resource parameters at a time of job run and you wait for them to go down when you again re-trigger the script. Or for example, if it's a parent job failure, so then you notify the parent job owner to re-trigger the script to identify what's the failure reason and then come back to the child job to rerun. And so on and so forth. So the data engineers had to go through the job logs, identify the reasons for failure, and then re-trigger the scripts accordingly. Often the job logs, if you can obviously imagine, they are unreadable machine content, which are often 10 to 20 pages long, right? So there is no easy way of searching it. You can try doing a control F, you can try doing like a string search, but because these job logs are quite contextual to the job, or the logs are quite contextual to the query, to the context, the job logs actually change a lot. And because if you're trying to predict an anomaly while the job is running, the problem again has to be a low latency, or the solution has to be a low latency solution, because your solution to identify or predict an anomaly cannot take more than the job execution time itself. And that is where the three challenges make this problem really tricky and quite interesting. The potential impact of this particular problem is that we had to invest separate set of engineers on weekdays and weekends to just monitor these jobs and identify and rerun those scripts. So, which kind of is a boring and a repetitive process. The idea is how do we move away from that, create a more intelligent way of identifying why the job has failed, and even predict if a job is going to fail based on the parameters when the job is run. Yeah. So let's look at the approach. What are the key elements of the approach? And I'll talk about, and I'll focus on the ones which focus, which deal with NLP and machine learning. So there are 4 elements to the approach, right? So the first one is breaking down the logs into different steps. So a log file, as you would imagine, is a large chunk of text. How do you break it down into different set of steps to ensure that each step is fed as a different set of information rather than passing all the content as one large chunk of text, right? That is breaking down the logs into steps. The next part is using these steps to predict whether your job is going to be a failure or not, or it's going to be an anomaly or not. That's the anomaly prediction part of it. The third part is if the job has failed, you look at a certain set of patterns to identify the root cause of the failure. And then based on the root cause assessment, you do a self-healing of these jobs through automated retrigger. So these are the 4 steps which are followed to identify whether a job is an anomaly or not. A lot of NLP is used in the first step itself, right? So let's go through it. So I think we have some time. Let me go through a little bit in detail on each one of these steps. So if you look at the step breakdown of logs, right? How does that work? So you have a large log file which is raw and there is no content or no readable context within it. So how do you break it down into steps? You essentially use the timestamps at the start of the line. You create a custom functions which essentially go through the first few characters of your individual lines and try to identify if it's a timestamp or not. So now there are multiple types of timestamps. There are timestamps across different zones. So your inbuilt function should be able to identify if the timestamp or not, extract the timestamp from it, and then ensure that it is aligned with the same time zone on which you're operating. So that is one. Then what you do is when you're creating these timestamps, you ensure there are certain set of exclusion rules which you need to follow to ensure that your step breakdown mechanism is working correctly. So how do you do that? You look at timestamps in line n+1, and then you compare them with the timestamps in line n, right? So we need to ensure that the timestamps which are generated in line n+1 are greater than the timestamps in line n, and the difference between the timestamps of two consecutive steps should not be more than 1 hour. Now, how do you really establish that, or why is this rule applicable? Is because generally the jobs will have a typical execution type of around 30 minutes to an hour. So an individual step itself should not take the full average duration of a job execution, right? So that is where we have ensured that the timestamps being generated are relevant and they're correct when we're identifying step n-1, step n, and step n+1. Finally, if you look at the long duration steps, so there will be steps which are taking say more than 20-30 minutes to run. What we also want to do is we want to deep dive into those particular steps to create further sub steps, right? So you have step 1, you have step 2, which is fairly bigger, and then step 3 and step 4 as a visualization. So what you want to do is you want to further break down step 2 into sub step 1 and sub step 2. The idea is that you don't have large chunks to comprehend in one go. You have smaller chunks which can be passed through your NLP algorithm later on, which we'll talk about when we are identifying the anomalies or predicting the anomalies. Right. So finally, just to visualize, because not all business owners will be able to appreciate each step, what we also do is we do a simple Gantt chart visualization wherein we plot the steps, we plot the substeps within it, so that we can see the sequential order of execution of each of the steps and substeps. So that's one. The next part is then focusing upon anomaly prediction. So how do you do that? Now, once we have these steps into place, these jobs are run, say, on a daily or a weekly basis. So what we do is we look at last 10 to 20 runs of the job, right? Right here it's 10. We also looked at 15, 20 in some other particular cases. And you compute some very basic metrics out of it. For example, if step 1 right now in the particular run is taking 10 seconds, how much time did step 1 take earlier, right? What is the mean of execution time of step 1 across the last 10 to 20 iterations? What is the standard deviation, and so on and so forth. So based on that, you can identify whether the current step 1, while the job is running right now, is it taking a lot of time when compared to, or taking very less time when compared to the previous entrance. The second part is looking at content similarity. So this is where not just looking at the duration of the step, you also look at what are the messages within the step, right? If you have ever looked at a log file, you would obviously know that within each step you will have either it's a step regarding resource initiation, it's either a step regarding your script trigger, it's either something about your resource being allocated or released, or your query being broken down into multiple subqueries. So each step also has a meaning associated with it, which is not very intuitive in the first go. But what we want to do with this particular process, we want to identify what is the content in that step, and then compare that what that particular step content would have been in the, or was in the last particular say 10 runs. So if step 2 is generally allocation of resources and successful allocation of resources, so we see that that content being the same across last 10 runs, and we see what is the content for step 2 in the current run. We compare those items to identify it as a deviation, right? And both of these factors are considered together to establish whether a particular step is an anomaly or not, and whether a particular execution which is happening right now is an anomaly or not, right? So I just want you to deep dive into this particular part a little bit more so it's clear. So let's say you have a substep. So you have step 1, step 2, and you have broken down into substep 1 and substep 2, which was the outcome from the first item in our approach, right? So this one. Now, what we do is there are two parts to it. So one is for each, for the say for the last 10 iterations, we identify what was the time taken for step 1. So average time taken, for example, was say 10 seconds, and the standard deviation of that time was say around 2 seconds. Again, so for step 2, how much time does it take on an average, and what's the standard deviation? And again, for step n, what's the average time and what's the standard deviation of the time? And then based on that, you create some thresholds. So again, it's mu plus minus 3 sigma. You can vary it. We looked at these constants to identify um, like whether this particular pattern is working or not. So that is a threshold which we use. Uh, On the content side of it, how do you do a content similarity? So what we did there was simple stuff. So we did text cleaning, so removal of stop words, we removed some punctuations, we excluded non-English vocabulary words because if you would imagine a log file has a lot of these underscore words which really don't have any embeddings in most of the NLP models. And then we ensured that it was case consistent. We use the all-mini N6V2 model to generate the embeddings. The reason why we did this was because this model is tuned for content similarity. It has a very low processing time and it has a very good performance. You can see the details in a link which I'll share later. And what was done was we look at the average of embeddings for step 2 across last 10 runs to create kind of a embedding reference for each step. So you will have you will have an array, or you will have an embedding matrix for each of the steps, which can be used as a reference on what the content should look like. Right now, once you have these two, so you for every step from the last 10 runs, you will have an expected duration. So step 1 should be between 4 and 6 seconds, and the step 1 should look like this in terms of the embedding matrix. Step 2 should be yeah, so it should be between 11 and 41 seconds, and it should have a embedding generation or embedding matrix as such. So these are the two reference points you will have. What you will do is you will see whether the step when the code is actually running, or the job is actually running, whether the step is crossing either the threshold or the similarity score of the embedding matrix is very low when compared to the last n iterations. Once you have this assessment, you can use it to flag whether the step is an anomaly or not. And once a set of steps fail, you can essentially say that the job is going to be an anomaly, because a lot of time what happens is that the job gets stuck. So the owners get only notified, say, after 12 or 24 hours of the job being stuck. What this will do is this will send a real live or a live alert even when the job is running, that there are 16 steps in your job. Step number 14 is deviating way too much from the expected behavior from the last 10 runs, and hence we are predicting that the job is going to be an anomaly, right? So then that is how the anomaly prediction model works. The job failure and root cause analysis. So this is the last element or the last piece of it. What we are essentially saying is once the job has failed, and this is based on the flagging from the internal systems itself, what we do is we have some set of strings which relate to the types of errors in that particular job. So if it's a syntactical error, you will see a particular string. So this is simple as even. So like there's I don't want to get any fancy terms for it, but yeah. So you will have a set of strings for syntactical error. This is a set of strings for resource usage, a set of strings for parent job failure, and so on and so forth. We also give a flexibility to the data engineers to create their own custom errors, which they generally see when they run their jobs. And based on that, once you have those patterns and once you have those embeddings, or once you have those list of strings, you can do a root cause assessment and then re-trigger the scripts accordingly. So what we asked the data engineers to do was, if it's a syntactical error, we can at our backend we can correct those syntactical errors very quite quickly, because it's either a missing bracket or there are some SQL statements missing. Validate it before we rerun it, because we want the data engineers to know what the revised query looks like. The second part is in terms of resource usage. So if there's a resource usage, we wait for the resource numbers to go down before we re-trigger those scripts. So that is the second part which we do in terms of script re-trigger. And if it's a parent job failure, again, we have identified for each child job what's the parent job, and we wait for the parent job execution to complete before we run the child job again. So these are the set of re-trigger scripts which have been executed as a downstream process from the anomaly detection model. Finally, in terms of the methodology, we had picked up a set of 20 jobs which had 1500 plus runs of it. What we did was we tried to establish whether the model is able to predict an anomaly or not. And again, you see that the model was able to achieve a 90% recall, close to 80. Sorry, it's not a 82% false positive rate. It was less than 20% false positive rate. My bad. And for nearly 1.5k runs. So uh, that is the kind of performance which we observe from the particular model. And the compute time was also fairly low. So you will see that the compute time is only 10 milliseconds, which when integrated as part of an API was fairly low when compared to the other systems. right? So those are the results from this particular model when they're predicting the anomaly. When we're trying to assess what's the root cause of the job failure, we're looking at the kind of strings we need to expect, or the kind of embedding matrix which we need to expect, and the like, because this is the most straightforward use case, the precision and recall numbers are quite high, right? So the formula numbers are quite good from the model here as well. So that's it. So these are the two use cases which I wanted to cover. I think I'm right on time. I have 10 minutes for Q&A, but I hope you're able to relate to these use cases and understand the performance of this particular model. Yeah, I'll give the mic back to the analytics with the folks. Team, do you want to chime in, or should I just start with the Q&A?
Paritosh, you can start. You can start.
Okay. So the first question is from Samiksha. So real-time use cases of anomaly, like in this scenario, in which industry the anomaly detection is crucial. Okay, so real-time use cases are especially important where the subsequent set of downstream processes are immediately triggered based on the current event. So say if you have an event X, think of it as, okay, let me give an example from actually manufacturing so that you're able to relate with it. If you look at steel manufacturing, so there are certain set of processes which need to follow, and at every step, you need to evaluate the percentage carbon content in your steel. Like that's an important metric, or in your hot molten material when you're trying to establish whether what grade of steel will you get, right? So the carbon content in your molten metal is a very important indication of what kind of steel will you get, right? Now in each process, at the end of each step, you will evaluate the carbon content. Now what happens is that if you get a very lower grade molten material at say at step 3 out of say 10 steps, right? All your subsequent 6 steps or 7 steps which are going to happen will work on a lower grade molten metal. And what will that do? That will essentially spoil the resources for the particular factory. In certain contexts, each batch takes generates requires at least 50 crores of raw material usage. So you're spoiling 50 crores of raw material if you don't share the anomaly quickly, like say within 5 to 10 minutes. So those are the cases where your real life or real-time detection is important. And even in the case I talked about before, if a particular process n fails and there are certain n processes n plus 1, n plus 2, which are dependent on n, these processes will automatically fail because the process n has failed, right? So we need to predict it real time. Those are cases where it's important. I might say the pre-processing task, post-processing, or after creating the model. So I have a question from Ashwin. Anomaly detection is the pre-processing task / post-processing, or after creating the model, this process is carried out. So anomaly detection can happen after the like I mentioned. So it's either a detection or a prediction. Usually, you detect when all the set of events have happened, right? So I'm not able to understand whether it's a I think processing is pre-processing, post-processing not applicable in this particular context. But if you're trying to detect an anomaly, you'll have to let all the set of events which have happened before to happen after that, or to essentially detect. Sorry. And if you want to predict, obviously the event shouldn't have happened before you make the prediction. So it depends on the context on which you're operating. Sir, why? So we have a question from Arun. Sir, why software engineer is required to write a program or test if a AI machine can do it right? Yeah, so that's the so to your answer, Arun, that's the ultimate intent of this. So this is an application of AI and machine learning, which is able to automate the processes, the checks, and implement a self-healing layer, trigger a custom script based on what the essentially the root cause of the problem. So this is an example of that itself. And yeah, and that's it. Those are the questions. Okay, sorry, and we have one more. So is it an unsupervised task? So it again, so there are
anomaly detection can be supervised, unsupervised, or semi-supervised. Again, it's context driven. In cases where you have a lot of training points and you have, say, your features which can help you predict the anomaly, you can create, say, an isolation forest model and predict a data point as anomaly or not, right? But in cases like the cases I talked about, the NLP model, that will not really be a very predictive model, but you have to create the features out of the NLP, out of the log files, out of text, and ensure that the subsequent data points follow a pattern before you call it an anomaly or not. So that is where it becomes a semi-supervised task, right? And in certain cases, like the first case which I mentioned, where when we're just feeding the data points, you're not training any model as such, it's completely unsupervised. So it can be either one of them. Okay. Okay, we have a question from Rahul. Hi Paritosh, great session. Could you let us know how you approach a particular nomenclature problem in terms of which technique you start with first and the process you go through to arrive at the techniques that work best, least complex? Okay, so there is no one answer to this. There is no one answer to this, but the way it's done is, one is obviously before you start implementing a problem, you identify the constraints you're working with. The technique essentially is dependent on what are the constraints you're working with. Is latency a problem? Is the type of data a problem? Is the context a problem? Right. So what are the constraints you're working with? What kind of data do you have available? Because each technique will be, so if you look at an isolation policy, you need a large number of training points to build your model. But if you create a rule-based techniques based on, say, previous and data points, that will require lesser number of data points. So you will look at what type of data you have available, what's the volume of data which is available, how fast you need to make your predictions to establish, and then filter out what, and then you do a research to identify what techniques are available to trim down what possible set of techniques might be applicable. Once you've trimmed down those possible set of techniques, it's a matter of testing it and doing a very thorough assessment of what's the performance metric from each of those techniques to establish which one should be used for. So that is how I would generalize it. And yeah, and that is how you can approach any kind of a problem, be it anomaly detection or anything else.
Guys, please post your questions in Q&A, not in chat box. So there is one more question from Alok Shinde. He wants to ask you that how to detect anomaly in text data in PDF.
Okay, so for text data in PDF, I might be a little bit off it, but there are standard Google messages which can read text from PDF files as well. I would love to just do a quick Google search and tell you that, but we did this once before. You can just read the text data from the PDF file. Post that it's like any standard NLP problem. So yeah, that it should never be a problem. So once you have the text from the PDF file, it you can just process that and move forward. There are certain cases where, if, for example, if you have a set of scanned PDF pages, it becomes difficult. And I've seen those before, or if you have cases where you are scanning handwritten files versus, say, text files, there are again inbuilt packages which can process it. The only thing you need to ensure that when you're reading those files and you're extracting content from those PDF files, the content is accurate and it's correct. There's not much deviation when you're doing an importing the data. Okay, we have a question from Gil Halberstein. I hope I've pronounced that name correctly. So how do you balance your model? What steps to use? So if you can elaborate a little bit more on what you mean by model balancing. Like, there are different definitions for model balancing. So I just want to ensure that I'm talking about the right context when I'm answering the problem. Are you talking about generalization of the model across different scenarios or use cases, or is it something else? Okay. Few failures, lots of not failures. Okay, balancing. Okay, got it. So See, anomalies by itself are itself will have obviously low failure rate. There are multiple ways to balance it out. Either you can do if you're using, for example, say a isolation forest, or if you're using a normal random forest model, in fact, for a particular example, you can just do subsampling. You can choose certain records and then increase the presence of your ones. That is one. There are multiple use cases where SMOT is used, which is synthetic sampling. That is two. But in this particular case, what I would want to ensure is that the model I create, it looks at failures and it looks at the volume of not failures or the successes as well. So I would not do a lot of balancing when I'm creating the model. I would ensure that the failures are captured correctly. And I would ensure that the features which I explain the failure are also captured correctly. Right. So that's how I do it. Like generally, you would use SMOT or you would do undersampling, but yeah, in this particular case, I would limit the amount of undersampling I would do when I'm executing this use case. So another question I have from Monali Roy: How does anomaly decomposition predicted modeling? How does anomaly decomposition predicted modeling of data conjugate equipment in use case? Manali, I'm not sure if I followed the question correctly. Could you type it again? But it is the next question. I have one from Rajkumar. Can you please share how these logs were formatted? What kind of information was logged along the timestamp? Was the log format decided earlier, or you adapted the NLP process on the logs that were available? So these log files, like you would imagine any Spark jobs, they contain the timestamp. They also contain the message in that timestamp. So what happened on that particular timestamp? Was it like job execution? Was it resource allocation? Was it something? So it was a long, like say 3 or 4 lines of machine content which is not really readable. In terms of did I have the log files available with me? Yes, I have the log files available with me when I was creating when I was finalizing the approach. And that is how I customize my data cleaning. That is how I customize what model I'm using for embedding to generate those embeddings. To ensure that when I'm creating the embeddings, I'm really reflecting the content within that particular step. So yeah, that was available. Okay, I have an anonymous attendee who is asking me, have you seen any cases where the techniques are adapted and extended to bias detection? Yeah, there are cases where techniques can be accepted to bias detection, but I would need more context on what type of problem you're trying to solve to maybe generalize the answer there.
I think now we can wrap up the session. So thanks a lot, Paritosh, on behalf of Analytics Vidhya. I would like to thank you for devoting your time and for delivering such a great session. I'm sure it was insightful, very comprehensive, and appropriate for lots of experience level. Hopefully, we can conduct more session with you in the future.
Yeah.
Thank you so much. Thank you so much.